Soda's also sick.
Okay. Looks like we're going live. How's that?
You make them like Thursdays.
CPM stuff 5-3.
Just checking. So those of you joining online, we're just checking the audio, making sure everything's going well. Okay. I'm hearing good things from across the room. It does say poor connection. What does this mean? Okay, just bear with us for a moment. Actually, I never had it say poor connection, so what do we even do there? Not receiving nothing. What? What?
My boss isn't speaking. Right.
Good parents.
No.
I think my connection is fine, surely. This is.
Oh yeah, I'll find you a drop in this week. That's the whole thing, right?
Yeah. I don't think we'll go for that one.
Yeah.
How do I turn poor string quality into excellent string quality? It's never been poor before.
Like, what did it look like on your end?
Well,
It's very
Are there any issues that you're
four
in?
on the side.
Yeah. We are going live.
It's like, why is not 480 degrees here?
It's like usual. It's good. Freaking everyone else, sorry.
I'll put a sign up saying this is not hot.
Yeah,
We can put the banner up. Okay.
Wait, maybe get that banner out. So
Yeah. We might get started then. I'll just monitor the video stream if there's any problems.
Alright.
I might point it this way so I can see what you're doing.
Yeah.
And I think we'll be good. Alright.
Hi. So yeah, today I'll just go over my honors thesis. So what I did it on was the distribution and mixing properties of modular exponentiation, and I did it with Dr. Igor Shvangovinsky. So I finished this last term. I'm currently unemployed. So yeah, let's get started. So yep, I think it's done. Right, so yeah, just some background, like the title sounds a bit fancy. Really, we're just dealing with the exponentiation map. So we're going to use gamma. So gamma of x to be like g to the x modulo n. Cool, and we're kind of just focused on studying this for like, why do we care, right? So it's kind of important because this is actually one of the things in maths that are used in like real life applications, mostly in cryptography. So a few things that are probably pretty common are like the RSA encryption algorithm, DSA, which is the digital signature algorithm, and also linear congruential generating, which are for random number generation. So,
Are you looking for mapping analytics? Yeah, it's not yet.
not yet. Signs there. I don't know what they are, sorry. Sorry. Signs are not marketing. I think they had a class that should be here, but maybe we kicked them out.
Marking and marketing.
Yeah.
Writing down.
Yeah, so
like one
slide.
thanks.
Like, so it's a very common thing we use for like a lot of things, but then like the thing that makes it interesting is that like we actually don't know a lot of interesting properties about this thing. So for example, like if you take it's very hard to undo. So what I mean by that is if you were given g and n, which are like the base and the mod, and then you were told to get to a certain number, like power g to a certain value. So like given a value y, what value of x gives you g to the x and y? We actually don't know like how to get that very efficiently. And that's something that's quite interesting. So this is called the discrete logarithm algorithm. And this is actually the reason why like this thing being hard is like these encryption algorithms actually use like this function at all. So like despite so we don't know, like there's no good algorithm to do it, but we also can't actually prove that like this is actually hard. So we haven't been able to formally prove it's NP hard or anything either. Which is why this is like kind of incredibly interesting. It's like 45 years of like a bunch of people who are very incentivized to break this thing because they would make a lot of money doing this by just cracking open every bank account in the world and taking all your passwords. But like despite 40 something years of that, we're still good. So yeah, this is why like we want to care about this. So now like that's why we want to study this, and the main thing is yeah, I guess some preliminaries on this. So some notation that we're going to use. If we use Zn to denote the integers modulo n, and sometimes we're interested in the order. So if you have a prime as the mod, the order of a element g is the smallest integer that when you power g to that power, you will get 1 back. And if there's a special case where it's a what we call g a primitive element or a generator, if the order is p minus 1. And what this means in this case is that if you take all of the powers of g, you will actually get all the remainders that are non-zero from 1 to p minus 1. And so a bit of like extra notation that we're going to use for this is some asymptotic notation. So we'll say that f is less than g if there is a constant such that like when x is sufficiently big, f is always going to be less than a constant multiplied by g, and that constant is like predetermined in advance. Some more of the comp sci people will notice is f is big O of g. We also have little o of g, which is kind of the opposite, where as x gets large, f of x is a lot smaller than g of x. Cool. And finally, we say that g is the asymptotic formula for f if their limits is of f of x over g of x is 1, so that means they're basically the same size as x gets big. And we also denote this by is sort of approximately g. Cool. All right, so the first like problem we're trying to tackle is if we let like p be a prime and g be a generator, and we want to find the number of points, number of solutions to g to the x is equal to x plus y mod p. So what this actually means in practice is, wait, if I use the whiteboard, people on the online can't see it.
That's fine. Just
Okay,
try
yeah.
to. Yeah.
So I don't know.
I've seen most of it.
So it's like if you have g to the x, what I'm interested in is like if I take x, so and I map this to g of x, mod p. How close are these two things? So then y is like trying to tell me how close. So I want to know like for how many values of x is this distance mod p at most mod h. So this is the thing that I'm interested in. And like what leads us to be interested in this is we use this function as in cryptography because we believe it's kind of random, right? And so we want to explore the like how random stuff is. So a good way of exploring randomness is just look at how the function is distributed. So this is why we do stuff like this, because the more we find out that it is random, the better it is and the more secure it is. And if we find out that something that's not random, that leads to possible breaks in like your encryption algorithms in very certain cases. Cool. So yeah, how often is g to the x close to x mod p? And yeah, what's the behavior of this like as h goes from 0 to p minus 1 over 2? So if you imagine like how this works is like if I have a line this is from like 0 to p minus 1, and this is my x, and then this distance here is like this is like h. So I'm wondering like how often does g of x lie on this intersection? And so if you imagine when it's like when h is 0, then it's like how often is g to the x equal to x? Probably not very often. How often? And then when h is p minus 1 and 2, then it's the whole length. So then it's going to be every time. So in some sense, there should be some function from like from that goes from 0 and then it ends up to like p, right? Yeah. So that's but we don't know really what's happening in the middle. But if it was random, then we expect that like g to the x will land kind of randomly. So then for a given h, we expect it to land in this interval like 2h over p of the time. So out of the P like trials, we expect like 2H of them to land here. So that's kind of the expected amount if it was random. And so we want to see how close it actually behaves to this. Cool. So first, like some existing results and related stuff. So one of the things that have been done is fixed points and also short cycles. So it's a very similar idea to this, where we want to see is like if you have an x and then you power it k times, can you get back to x itself? So this is like x and then g to the x mod p, and then next is like g to the x mod p. And I guess like what's interesting and non-trivial about this immediately is that if P is a generator, the exponent has modulo P minus 1. Has like it repeats P minus 1. But here we're doing something like P. So like you don't actually get like cycles particularly nicely, which is what makes this a bit funny as well. So yeah, we have some results of this. A lot of them by Eagle himself. So the first one's so easy. So this is fixed points. So how often is g to the x converted to x? And yeah, this one is actually not too. So you can prove that it's like approximately root p. This one's not too bad. I'll show later. It's actually this one's significantly easier than all the other ones. Like yeah. So now but even then actually you think this shouldn't happen very often, right? Like g to the x probably can't be x that often. But actually you can see this value is root p. It's not that small, right? It is small, but it's not as small as you think it should have been, which is 1. But then once you get bigger, it becomes significantly worse. So this is a short cycle, so of 2. So if you have g to the x twice, and then you apply this twice, how often do you get back to itself? And actually this it's actually p on log p, which is p, right? And that's it's actually this is a fairly weak result, and it's which is surprising for something that sounds not too complicated, right? And also the C of g here, the constant in front of this actually depends on the size of g. So for smaller g, this is nice. But if your generator that you choose is big, then your bound gets worse. Cool. What about the 3 things? So someone proved that it was little over p. This is the best this is the best thing we have, right? And this is for a fixed g as well. And actually in Eagle's paper earlier, in the paper where he found the p over log p1, his bound for this was 3p over 4. It's it's big. So yeah, this is actually decent, I guess. You know that it's small and it's not going to be a lot of them, but it's a very weak, not a lot of them, right? And once again, this is also for it also depends on g. So as you can see, this is for some reason quite difficult. Any guesses for 4? Some people would have seen it already. Yeah, that's no result. Yeah, so actually, we don't know what happens for when you go to bigger cycles. This is quite hard. Yeah. Okay, so back to our problem. The main kind of trick that we're going to be using is this thing called exponential sum. So we'd call EP of x to be the exponent of 2 e to the power of 2 pi I x over p. And we have the sum, which is you sum over all the different possible powers or the possible elements of mod p you have from 0 to p minus 1. And you put EP of some parameter and then g to the x minus 6. So these sums, generically of EP of ax, and where x cycles from could be 0 to p minus 1 or whatever you want. This sort of thing, is called exponential sums, and they're fairly common. And the reason they're fairly common is for this other inequality I'll show later. But a lot of this just boils down to trying to find good bounds for this for good bounds for this, where inside here you might have something, you might have like a function of x instead. And yeah, we'll see how that gets used later. So here we have this result, which is that SP, like the sum over here of A is actually going to be like less than p to the half plus A. Why this is useful is that like these two bits are kind of like fairly like if A is small, and then p to the half is quite a good bound compared to like, so a trivial bound for this, right? Each of them is at most 1. So if you sum over p minus 1, you get p. This sucks. But if you do like A, if you make it smaller, you only get root p, which is, and here we're thinking about p for very, very large p, right? So like, in practice, people use like 2 to the 256 bits to 500 bits. So this is very like huge p. So root p is actually quite awesome.
But that GDS was like it's in one.
So the trick here is that it doesn't actually. So at the because it's like
Yes.
it would be, and you have a 2 pi I. So this is actually periodic.
What is A?
So A is the parameter you want to pick it at the SP. Like so, it's like SP is a function, and it's a function in A, and then where when you put in an A, it cycles through all the x's, and then it sums over that. So this is a function in A.
Yeah.
But it's built on the exponential things.
I'm gonna assume that we're gonna know why we have the A there. So that's
Yeah.
sorry.
So this is the like main sort of like this is the main tool that we use, which is this inequality, and the specific details are not like too important, but what it's basically showing you is that in the top we have this absolute value, and what we're saying is that MPG of H, which is the number of points that we're trying to count, and what we're subtracting here is actually the total number, is like the expected number of points that we have, right? Because it's 2h, it's roughly 2h. So this is actually like, we're saying that the difference away from the expected number is bounded by this expression over here. And this expression here is contains the SP value. So these like types of, so this sort of like error is known as the discrepancy. So we'll use this term later as well, the discrepancy. So it's like kind of like how far it deviates from a uniform. And why this SP of A, like why this sum actually comes in. Like a little bit of motivation because for the like how the inequalities roughly work. But that like I was shown by Eagle is like, imagine you're counting places where you sort of have a function that's like kind of a signal function where like it's like 1 if this condition is satisfied, like 0 if it's not. And then if you want to try to count how many times something is satisfied, then it's like you're kind of counting like a function. You're trying to like, you can kind of think about it as taking the integral function like this. Now obviously this sucks, taking integral, right? So what we can do is we can try to do we can try to approximate it using like Fourier series. And then, so like for a particular signal, you can approximate it with like 1 Fourier thing over, and then like 1 Fourier thing under. And like you can sort of tie in these two and to get an approximation for what the integral should do. And actually, yeah, this is how, I think roughly this is how the like exponential sums turn out into, because those are Fourier coefficients. But anyway, so what does like this, why is this useful? Or how do we use this? So the idea here is that like, actually your choice of A, like this inequality, so we have a less than or less than sign. So it's like this is big O of delta, right? And the like implied constant here actually does not depend on whatever choice of A you use. So that means that A is a parameter you can choose freely to optimize this bounding. And actually, so that's what we're able to do. So by picking A nicely in order to sort of balance these expressions, and then also using the bound we had for SP of A from earlier, we're able to get this expression here. So what is this saying? This is saying that this our thing that we're trying to count is actually equal to the main term plus and also a constant of like an error term of size root p times p to the quarter times h to the half. So obviously, yeah, the error term does depend on h. Cool. So yeah, like this error term is nice because it doesn't exceed O of p to the like 3/4, which means it's actually always like sort of little O of p, and that's good. Like sometimes if you like mess up, your error term is going to be bigger than your main term, and then that's just bad. So we want to see when that happens. Yeah, so our main term is O of h roughly. So if h is, as long as h is just a bit bigger than root p, then this error term is actually is going to be small compared to main term. So we have a asymptotic formula over there. And then when it's smaller, the error term, yeah. So here when h is small, your error term is going to be bigger than the main term. So which means that like you do get a bound, it's just not the bound that you're hoping for, and it's a bit weak. Cool. So we can look at some numerical analysis of this. So what I did here was I just looked at I just plotted the discrepancy of this like across from 0 to p minus 1 over 2, and it's normalized by p. And we see that like the movement's like fairly random, but actually also that the size of the error is actually like pretty small. So we were thinking of an error term that was like p to the half h to the quarter, right? So this is like when p gets bigger, it's roughly when h gets bigger, it's roughly like p to 3/4. But actually these errors like over like a couple, so this was 20 primes, I did this over 1,000 primes. They're roughly like actually within, so the two red lines are actually like root p size. So these are actually like, they end up actually just being like this section here in terms of error. And that's like good. So that means that like, it actually does follow the expected, like, so we expect it to be linear in a random map, right? And it actually is. And the error like that we see in practice is actually like very, very small, which is good. And yeah, so this is one like biggest ones and smallest ones, and it still kind of falls into this range. So one thing I did say earlier was that our bound was weak when we looked at root p, right? Like when we looked at h smaller than root p. And if you look at this, like these primes here that I picked were like approximately 10 to the 9. So where is root p? Like where is root p over here? Right? It's like this tiny line over here. So we can't really see how it behaves in this small area when we look at this map. But if I shrink it down to like what's happening in the square root of p area, so these like plots are just what's happening between like 0 and root p for the same like this difference between this and the expected. And actually like with these two lines are 4 times root h. So they actually fall like, so surprisingly like our bound before for the for the small cases was root p. But actually from the numerical analysis, it could be as tight as like root h. So if you want to think about comparing how big these are, right? Keep in mind this right now, this is under the restriction that h is less than p to the half. So this is actually much smaller than this, which is interesting, and we can't actually see that from the analysis, from the like proof that we did. So yeah, this is something interesting, and which means that like overall maybe like we can actually improve this to just like root h as the error bound, which would be quite interesting. Cool. Alright, so we'll move on to the second problem, which is kind of looking at this but in more dimensions, and we're looking at them as consecutive powers. So we take u0 like u1 and so on to be a sequence of consecutive powers. And then what we can do is if we take a dimension k, we can like group consecutive k tuples of these and consider them as points in a k-dimensional space. Cool. And so what we can also do is we can normalize this and shrink it down to a unit cube. So inside a unit cube, this is like from 0 to 1, 0 to 1. You can put these points as like points inside this unit cube. And now the question is, okay, once again, so why do we care about this? We care about this because, like, for randomness, it's not enough that, like, if you look at all of your points, they look random. You also don't want to have your, like, consecutive points be, like, correlated in any way. And so if you look at in a different dimension, so what's a fun example of this? Yeah, I guess if you took like a easy example, if you just took like powers of 2, like, or 8 and so on, like, what am I trying to say? Yeah, so yeah, I guess if you took stuff like this, what be, and 2 was generator, right? Like, that would hit everything, and you're like, hey, well, if I don't look at them in any particular order, it's random. But let's say you put them in 2D space, right? Where you take consecutive ones next to each other in 2D space. What you're going to notice is that a lot of them are going to just lie on the line like 2x, right? And so then what you're going to have is like lines in your cube, which is not random anymore. So this is why like this by itself is not a great metric for like how random something is. You also want to look at stuff in high dimensions. So here, that's what we're going to be doing with this. So yeah, we're going to call this function n to be like our counting function. So for a given point in our cube and a given radius, so a and r basically just give us a ball of radius r inside the cube. We want to count how many of these points actually lie inside this one. And once again, it should be what we expect is the volume. So here we use this discrepancy. And what this is basically saying is like a of x is so x, you take any subset x, and a of x tells you it's like the count of how many of the points lie in that thing. A of x divided by n is the like proportion of points that lie in that wall. And you subtract by the volume because that's the expected number of points that you have, right? So, and then if you take the supreme number of that over like for some nice volumes, then you would get a notion of discrepancy. So yeah, this is basically a measure of how uniform a set is. So it's like, this is your space. You take like something nice. You count how many things are in here, divided by the total proportions, and you look at that ratio compared to like the volume. And it's like, oh, if it's close every time, then it's like somewhat uniform, right?
It's like the nice x, like the definition of nice. Is that like really important? Like is it like important that it's like on smooth, for example?
So okay, so here like the reason I'm just saying it's nice because like in theory you could cheat, right? You could just draw the circles and I don't want to do that. So most of the time in practice, what we're doing in this case, I don't write it specifically out. And most of the time, so the previous work was done when the volume we use are all like boxes, but people didn't do much on boards. And so in what I do, we look at the same sort of version of this problem, but instead of doing boxes, we do boards. So I'm restricting myself to just boards for the volumes. The problem with like doing any set is because when you have a finite number of points that repeat, it's kind of bad. Yeah, so we have some results in the discrepancy in boxes. So a box this is your like, I guess your intuitive definition of a box. You take two endpoints and you just extend out all of the axes to meet both sides. Yeah, so this would curse, right? So like, once again, it's not yeah. So actually, this is like a very similar version of the inequality for the 1D case, but this is just extended for 2D, for multiple dimensions. And like the specific points of this is not too important. other than the fact that like you have this thing over here, which is once again like an exponential sum. You're summing it over like whatever like distance that you want to sum over. And you're kind of like sum this expression over different like length vectors. So this thing looks really weird. In reality, we'll get a whiteboard mark thing. What it actually like, what the actual like expression looks like, which looks a bit nicer than this, is if you take, so if you take like a B, which is B1, B2, B, what I use, S, right? What we're doing is we're taking the like reciprocal of like B1 plus 1, B2 plus 1, BS. So like these two things, like and 1 over this, like these two things differ by like trace of constant. So if you want to think about it as a more like and nice analytical thing, then this is the expression that you actually want to work with. And what happens when you do something like this is that like, and basically you're summing this over a certain like, so the thing here is you're summing over the infinity. So all the b's are restricted by some value. And if you think about what happens here intuitively, if you fix the rest of it and you sum over one of these, you get like, so let's say you're summing from like the epsilon value is less than or equal to r, right? Then you kind of get a log r here because you're summing like the reciprocals of the r. So actually, if you sum over these independently, this roughly gives you some like log r to the s kind of expression. Which makes this like not terrible, like so you actually get something reasonably like okay here. And then you also have this. So like once again, why this is similar to the previous example, it's like for any integer r, which means that you get a r of any, you get to pick your r. It doesn't change the implied constant. This, as you increase r, gets more. This, as you increase r, you're summing over more things. So you again try to pick your r to balance these things. Cool. So here, like, there's a lot of bounds that you can have for the exponential sum. In this case, it's a bit more free because I've allowed, in the previous definition, I've allowed our G to no longer be a generator. It can have a different order. So you might only have like a subgroup of the stuff from 0 to P minus 1. And in which case you might get a different bound. So a lot of these just depend on what bound you end up choosing for your exponential sum. And this will differ depending on what you're trying to do. And so if you get it, like assuming you have some like bound for this, then you actually get this result, and being log r to the k is what I explained it. Cool. So on the other hand, like there hasn't been very much like stuff explored with boards. And then there was only one from a while ago in 1975 where they bound the number of discrepancy reports with Jn between two expressions in terms of the huge box discrepancy. And what we aim to do is we want to do it without using the box discrepancies, and we want to do it perfectly get a better balance. Cool. So luckily for us, someone called Haibing came up with a similar type of inequality for force. Unfortunately, it's like even more horrific. And so like the details once again are not as important. That was for me to work through for like 2 weeks. Work a day. For like I didn't work at all. But anyways, it's like once again, it's like you have an expression. This is you're choosing the notation is a bit different from the previous one. But once again, you're choosing the s. As you increase s, the top one gets smaller. As you increase s, you get more things to sum up from the bottom. Balance these things depending on what you're trying to achieve. Cool. But yeah, like the difference between these two is that this expression is far more annoying to just work with, especially because you have this min thing over here. So the thing that we actually use for this is we want to use this DOM, and this is going to help us with the bound. It's going to be a time in bound later. So we want to find the largest integer such that there is nothing. So remember, U is the a set of consecutive powers, and we want we want to find a the size for which nothing smaller than that size dots with U to be 0. Sounds a bit hard, but like if you imagine you have a vector a U, and then in your dimensional space, you have some vectors that will dot with this to be 0, and they're all integer vectors, so they won't be incredibly. They may not be incredibly close to 0. Like up here, you have a line. Maybe this is the first dot off, and then this within this ball, nothing is going to dot it with U to be 0, and we want to find basically how big this ball is, and this way we're going to W. So this gets used inside the proof, but I don't think I go through how it does. But what ends up happening is so maybe some intuition for why it gets used. This sum here, right? So with the exponential sum of something, right? Wait. Of some function of this, when the inside is non-zero, you're gonna get some we have a bunch of bounds plus a bound with something like root p, right? The problem that happens is when this is actually when the inside here is when a is 0, right? Or when something dots to 0 here, in this case m.u. So if m.u is 0, then when you're summing over this, you get a massive thing, you get t. The sum becomes t, right? Because all the terms are 1. And that's bad because t is big. So the idea for having stuff in terms of this w is that we know that as long as we restrict out s within this w, then we're only picking vectors inside here, and we're never going to have a sign. And that's important to control the size of the exponential sum. Cool. So yeah, with that, if we have the theorem that I had at the end is that if you have t is sufficiently big, in this case bigger than root p, and r is also sufficiently big in terms of t and w, then we get this expression here where the first term is the main term, which is 3 times the volume, and you have this zero term. Look, I tried really hard to make the zero term. This is so obviously now you have to the reason why I have these bigger than the reason I need this bigger than this is so that this term actually dominates this, if I remember correctly. Yeah. So yeah, which means that if you make r just a little bit bigger than this, then it will actually have an asymptotic fulfillment. So at this point, when r is exactly the second expression of here, these two are the same size. So then when r is a little bit bigger, then the first term becomes the biggest one. Cool. And also, actually, it turns so the thing with this w is that it can actually be quite small. And we don't actually have a good way. So we would like w to be for this w to be not something we think we have to concern ourselves with. For example, here, if w is sufficiently big, then we don't have it's not part of the consideration when we can treat our S right to optimize, treat our optimization. But the thing is w can be very small. As an example, let's say if g is 2. What does your vector look like? It looks like u naught, 2u naught, blah blah blah, right? Then you're okay, I wonder what vector when I dot with this is going to give me 0. 2 minus 1. 0, 0, right? Yeah. So here w is tiny. Which means that in the cases like this, you're going to have a bit of problems. So yeah, there are going to be cases depending on G where your W is very small. But actually, in the majority of cases, it is not too small. It is actually huge, so usually it turns out that like W is going to be at least p to the 1 on yes, on k. Like k is the number of dimensions. So it's not too tiny in the general case, but there's going to be cases where it is small. So actually, this happens for all but like little OP of G values. So it's like for almost all G, this is going to be true, which is nice, and it means that most of the time we can actually just get rid of that and relax it to this condition. Yep, so, and then we're using numerical analysis on this. So what I did was, here I just took balls centered at the origin of radius 1/2, so the maximum white picture. And then we looked at like what the discrepancies look like. And yeah, they're just like kind of distributed here. And you'll notice that the errors are not that big. What else have I done? Yeah, so what's interesting here is that if I looked at the ones with like this is the distribution of the primes I actually have. So it's kind of randomly bunched between like 1 billion and 2 billion. But then if I only restrict this to like discrepancies that are big, it actually kind of decreasing, which is interesting. So what that means is like as your primes get bigger, the proportional discrepancy gets smaller, which is what we hope for when we want something to have an asymptotic formula. And then, so now, we also did some random balls. So I took a ball and like put it somewhere else. I think the radius for the is here. 0.2 guess. I picked something so that the condition hold. But like yeah, I'll put some, and then we just put random balls in the box, and then saw how many like sections are in it. I think I just simulated like with some probability because I didn't want to count 1 billion points for every single ball. But yeah, it turns out like no matter where they are distance-wise from the center, they all look kind of similar. So it seems like there's no good meaning of like where the center is doesn't seem to have a big impact on what the discrepancy is going to be like for something of the same radius. And this is also over like a few hundred primes as well. This burnt like $200 of like free Google Cloud. That was fun. Cool. So yeah, just a quick summary. We proved some bounds for G of H for the almost fixed points, and for when H was bigger than root P, we found an asymptotic formula. And then we also looked at how it worked for higher dimensions, and also found an asymptotic formula when the radius is sufficiently big for the balls that we're looking at. As well as some future work, so yeah, numerical results, they suggest that like the bounds I found weak. We can probably get something better. And yeah, so in most of the time here, we were doing stuff with just primes. So maybe like if we looked at composite modulus, or non-primitive elements of, for the first one, for the almost fixed point, you might get something different, and it's probably also a harder problem to work with because primes give you. So actually, like one thing that a prime will give you that composite will not is this. The proof of this fails for composites. So you might have to come up with some other ways coming up with that. But yeah, these are other possible research topics that people can do. Cool. That is me.
Any question? Any questions online?
Oh yeah, you can check. I chat.
Have a look.
I think the proof of the thing, that one I kind of put it on. Okay.
I'll end the stream now though.
Yeah, it's fine.
Thank you everyone joining online.
Yeah, it's not.
Your ping.
Yeah,
thanks.
thanks.
It's ping. Wonderful. All right.
There you go. Better get ready.
There's a reason.
Yeah, but it's like kind of somehow